Welcome back to Physical Chemistry on Catalyst University. My name is Kevin Tokoph. Please make sure to like this video and subscribe to my channel for future videos and notifications. In this video, we're going to discuss a topic in solution chemistry, which is the thermodynamic parameters for mixing. And so, just to give you a brief intro, we're going to be using throughout this video the example of making a Jack and Coke, which most people are probably going to need after they finish a physical chemistry exam. And so if you make a Jack and Coke, what you do is you mix some volume of Jack Daniels, and you mix some amount of Coca-Cola. Okay, and it's not necessarily 1-to-1. It could be 2-to-1, 3-to-1, 1.5-to-1, whatever. But you're going to mix some amount of these, and they're gonna make a mixture. And we would like to be able to quantify the thermodynamic parameters for that mixing. And so we're going to look really at 4 of them. We're going to look at the free energy, that is delta G, the entropy, or delta S, the delta V, which is actually the change in volume, which actually is not just simply the sum of these two volumes, and then also the enthalpy, or delta H. All right? And we're going to do it for 2 cases. One is which we have ideal mixing, and the other is real mixing or non-ideal mixing. Okay? Now the first we're going to look at is the Gibbs free energy of mixing. So what's the free energy associated with basically taking some volume of Jack and some volume of Coke and mixing them together? Well, let's think about this for a second. When I mix these together, only a fraction of it is going to be the Jack and only a fraction is going to be the Coke, right? And so both the Jack Daniels and the Coca-Cola each have a mole fraction associated with them, right? And that mole fraction is given by this italicized X right here. And so what we would do is we would take the sum of the natural log of each of the mole fractions. Okay, so in our example here, we would take the mole fraction of Jack Daniels in here and take the natural log of it and add that to the natural log of the mole fraction of Coke in our mixture. Okay, and that's our sum of the natural log of mole fractions. And then we would simply multiply it times the number of moles total, and then the ideal gas constant, and then the temperature in Kelvin. And this whole thing then would give you the free energy of mixing. Okay, now one thing that I do want to point your attention to is that remember that because we're going to have mole fractions less than 1, because by definition a mole fraction has to be less than 1, let's say it's like 0.4, if we take natural log of 0.4, so any natural log of any number that's less than 1, between 0 and 1, that number is going to be negative. And so this sum right here is actually going to be negative. So when we multiply by 3 positive values, our overall free energy for any one of these mixing problems is going to be negative. Okay? So it's going to be spontaneous, theoretically, but we just have to calculate that. All right? So that's our free energy of mixing. Now let's look at the entropy of mixing. The entropy of mixing is defined as the negative partial derivative of free energy of mixing with respect to temperature. Now, we can more or less neglect the negative sign right now. We need to figure out what the derivative of free energy is with respect to temperature. Well, normally we don't have a function for free energy that's simple, but in this case we actually do. We just looked at it. And so we're going to take this function right here and differentiate it with respect to t. All right? Now, because these mole fractions are independent of temperature, and so are R and N, we just have a simple power rule derivative. All right? And so if we take the derivative of nRT times the sum of the natural log of all the mole fractions and differentiate that with respect to T, then essentially the T just drops out. And so if we then factor back in the negative sign, the entropy of mixing is going to be negative nR times the sum of the natural logs of all the mole fractions of each piece of our mixture. Okay? So these are the same mole fractions from calculating free energy. We have a mole fraction of Jack Daniels in the mixture and a mole fraction of the Coca-Cola in the mixture. And we just basically add up those natural logs and then multiply them times negative nR. Now, because remember this sum of natural logs is going to be negative because we're taking the natural log of a decimal, then multiplying by 2 positive numbers will still be negative, but then we have a negative sign out in front. And so generally speaking, when we're mixing more than 2 things together, or at least 2 things, our entropy is going to be positive. And that makes sense because we're going from essentially pure Jack Daniels and pure Coca-Cola. We're mixing them together, and so overall this is going to be more disordered than either of these pure products independently. And so the entropy should increase, so delta S of mixing is going to be positive. All right? Now, we're going to skip delta V of mixing, come back to that in a minute. I want to go to delta H of mixing. And this is actually going to come from one form of the second law of thermodynamics. Remember that we could express delta G as delta H minus T delta S. If we take that second law and essentially solve it for delta H, we get this expression. So the delta H, or enthalpy of mixing, is equal to the free energy of mixing plus T delta S of mixing. Now we can now do this because we have an expression for delta S of mixing, and we have an expression for delta G of mixing. All right. So first I'm going to take the expression for delta G of mixing, which is up here, and just stick it down here. That's nRT times the sum of the natural logs of all the mole fractions. And then I have to add on T delta S. Well, the delta S of mixing is negative nR times the sum of all the natural logs of all the mole fractions in our mixture. So that's this piece here in parentheses. But then it has a negative sign, right? And then I have to multiply by T because it's T delta S. So I have to throw this T right here. All right. Now, remember that this expression for the second law of thermodynamics, where we have, this is one form, delta H equals delta G plus T delta S, or delta G equals delta H minus T delta S. This equation is assuming ideal situations or an ideal condition. Okay, so when we calculate this delta H now, it's actually going to end up being 0. And as we'll see in a minute, that's only going to be the case when we have ideal conditions. But it suffices to say for now that for ideal conditions, when you actually add all this together, we get nRT times the sum of the natural log of all mole fractions. And if we pull this T inside here, this whole thing becomes identical to what we have over here. And so it's one term minus the same term. And so you just get 0. All right. So that's the delta H of mixing. All right. Now, before we get into these various conditions down here, let's actually talk about the change in volume associated with mixing. All right, so let's look at a simple example. And this stuff is not really for this presentation, but this picture will do fine right here. Okay, so let's suppose over here in red, this is our Jack Daniels, and over in blue, this is our Coca-Cola. All right, and let's just say hypothetically each of these is 5 milliliters. 5 milliliters. So 5 mils of Jack Daniels, 5 mils of Coke. If we were assuming completely ideal mixing, then the total volume when we add them together should just be 5 plus 5. So it'd be this situation on the far right. So it'd be 10 milliliters, right? But that is not always what happens, especially when we don't have ideal mixing. Sometimes there can be interactions within the solutions when we mix them, such as attractive forces. And when there's attractive forces of any kind, you actually have a volume contraction. And so instead of getting 10 milliliters, the combined volume may actually be a little bit less. Now this is sort of an exaggerated example, but maybe it's only 9 milliliters, which means you don't have ideal mixing. Because if it were ideal, 5 plus 5 milliliters should give you exactly 10 milliliters. But sometimes you don't get that. And say in this example where the combined volume is actually a little bit less than what we would expect under ideal conditions, this would be a situation where attractive forces within the fluid are predominating. If we added these together and instead got like 11 or 12 milliliters, then it would be repulsive forces within the mixture. Okay? But sometimes this happens, and in this case you don't have ideal mixing, rather it's real or non-ideal mixing. Okay? Now in any case, the change in volume associated with mixing you can define by this partial derivative. It is the negative partial derivative of G of mixing with respect to pressure. Now, it's only equal to 0 for ideal conditions. When you have real conditions, this change of volume of mixing is not going to be 0. All right, so now let's compare the two conditions, ideal mixing versus non-ideal mixing. Now, the nice thing is when you're talking about the free energy of mixing, it's the same in either case. So if you're asked to calculate delta G of mixing, it's just nRT times the sum of the natural log of all the mole fractions in the mixture, and it does not matter if you're talking about ideal or a real situation of mixing. Okay? And the nice thing from that as well is that Since the entropy of mixing is given as the partial of G with respect to T, that is the negative of it, G is the same for both, so therefore the entropy will be the same for both. It's going to be negative NR times the sum of the natural log of all the mole fractions. So if you're given a problem, you can actually calculate the delta G and delta S associated with this. All right. Now, these last two right here, the change in volume associated with mixing and the enthalpy of mixing. These are not really so much calculations necessarily that you do all the time. They're more conceptual questions. So you could be asked more or less to calculate the free energy and entropy, but given whether it's ideal or non-ideal, you could be asked what is the change in volume and what is the change in enthalpy. If you have ideal mixing, the change in volume is going to be 0. And what that means is that if you had ideal mixing, when you add 5 mils of Jack to 5 mils of Coca-Cola, you're going to get 10 milliliters. And so the change in volume, this delta V that we're looking at, what it really is it's the difference in volume between ideal conditions and then what you actually get in real life. Okay, so if there's no difference between what you actually get when you mix them and then considering it's ideal, then the change in volume is 0 and you do have ideal mixing. However, in this example right here, we don't get exactly ideally 10 milliliters. We actually get a little bit less than that. And so this means we have real mixing or non-ideal. And so in this case, delta V would not be 0. It would be a non-zero number because there is a difference between what we actually get in reality when we mix these and what we get from ideal conditions if we just added 5 plus 5. There's a difference here. And so now we actually have a difference in volume. And so for non-ideal mixing, our delta V of mixing is not 0. Okay? And it can be positive or negative. All right? Now, if you're asked about the enthalpy of mixing, if it's ideal mixing, the enthalpy is automatically 0. And that's because this form of the second law of thermodynamics is given for an ideal situation. All right? And since we know the expression for free energy up here and the expression for entropy up here, you can prove that the enthalpy of mixing is 0 for an ideal mixing situation. However, for non-ideal mixing, the enthalpy is not 0, and it can either be positive or negative, just like the delta V of mixing. All right? So these last two would be more conceptual questions, not necessarily a calculation. These first two for Gibbs free energy and entropy could certainly be calculations. But hopefully at this point, given our little example right here, the thermodynamic parameters for mixing make sense. All right. So thank you for watching this video. Please make sure to like this video and subscribe to my channel for future videos and notifications. Thank you very much.